now that we have introduced affine schemes and the spectrum of a ring, the next thing we want to do is to look at functions on such an affine scheme and what the Zariski topology is supposed to be. And so to state some analogs that we want to generalize, when X was an affine variety, then we had that A of X was a ring of coordinate functions on X. So we knew what a global function on X is. For such a function f and x any point in the space X, we knew what the evaluation is at this point. This would give us always an element of the field K over which we work. And finally, when we have an ideal inside this ring of functions, then we could define its vanishing locus inside X. And basically, we want to see how do we generalize all of these things. And so the first, the idea is very simple. So the functions on X equals the spectrum of R should just be the elements F in R. So this fits well with what we had before, that somehow the spectrum of AX should essentially be the scheme theoretic version of the affine variety X. And so then we already come to the next question, namely, how do we evaluate such an element of this ring at a prime ideal in the ring? Because, I mean, we don't really expect that we always get something in the same output, namely in the same field, for example. We will see that the target of the evaluation will actually have to depend on this prime ideal P itself. And so this is the next definition. If R is a ring and P is a prime ideal in R, then we define the residue field of P in the spectrum of R as, well, you take R modulo P, which is an integral domain, and then to get a field, you can take the field of fractions, so which is just the localization at the zero ideal of this integral domain. And this is certainly a field. It depends nicely on the prime ideal P. And so indeed, this allows us to evaluate now any F in R at this prime ideal P by just saying, well, you take the class of F in R modulo P and you divide by 1, and this gives you an element in this fraction field. So you can see this also as the image of F in R under this composition of maps, which first goes to the quotient R modulo P, and then has this inclusion in the fraction field. In particular, since this map from the integral domain to its fraction field, this is injected. And so somehow, if you have an element which evaluates to 0 at P, then it must have gone to 0 already in the first map. And this is equivalent to saying that F is contained in the prime ideal P. So F of P equals 0 is now equivalent to F being in the ideal P. Okay, so let's see some examples. First, our favorite example when R is the coordinate ring of an affine variety of an algebraically closed field. Then let's see whether we get back the evaluation, at least at points that we're used to. So if the point A inside X is a classical, just an element of this affine variety, then we saw that the associated prime ideal is the maximal ideal associated to A, in other words, just the ideal of all functions vanishing here. And then if you take this quotient of this full ring by this maximal ideal, you get a field already. And the field is just K itself, and the isomorphism just takes this class and evaluates it at A. That's the classical isomorphism that we saw in the context of the Nullstellensatz. And so since this is already a field, taking the fraction field actually doesn't change anything. You just get back K of P is just K itself. And then this composition here is exactly this map here, so which just evaluates the function at a point. So at least for these kind of maximal ideals, we get exactly what we were hoping for. So what about all the other prime ideals? We have seen the prime ideals in A of X exactly correspond to this ideal of Y, where Y is an irreducible subvariety of X. And then the full coordinate ring modulo the ideal of Y is just the coordinate ring of Y itself. And then what happens when we take the field of fractions, when we localize at 0? Well, we have seen actually that this is exactly the same thing as when you take this sheaf of functions on y and you take the stalk at the essentially generic point of y, or we call it the stalk at y itself. So we defined this notion of taking the stalk of a sheaf at an irreducible subset. And these were basically just functions which were defined on an open subset or in an open neighborhood of a subset of a point of this irreducible closed subset. And so in this case, you can check in this remark that this is exactly what we get by taking this fraction field, because it's the localization of this at the 0 ideal. And then we can interpret this stalk as just a set of rational functions from y to a1 of k. In other words, these are functions defined on some non-empty open subset of y going to the affine line a1. And then we see that what it means to evaluate an element f in R is just you restrict f to this irreducible subvariety y, and then you see it as a rational function on y. And I mean, because you started with an element f which is defined everywhere, this rational function is actually defined on all of y, so it doesn't have any poles. But so this is if we work out this definition in this case, this is what we get. So this was all still in this kind of familiar realm of affine varieties over a field, but we can also take more general rings. So for example, just the integers, and then a function on spec z would just be an element of the integers, it's just some integer number. And then what are the evaluations? We have seen that the possible prime ideals are either this ideal generated by a prime number or the 0 ideal. And so if we compute the integers modulo these prime ideals, on the one hand, we get z modulo pz, which is already a field, so it's its own field of fractions. And at the 0 ideal, we get, sorry, this is not, so somehow r modulo p, this here is equal to z, and then the field of fractions is q. So here you see it really makes a difference. We have to take the field of fractions at this point. And then what does it mean to evaluate at these points? Well, on the one hand, if you evaluate at these prime points, then you just get the class of this integer in z modulo pz. Whereas if you evaluate at this point, then you interpret this integer as a rational number. So here we see that in particular in this spec that the fields that we get are on the one hand the z modulo pz, which are the field fp with p elements. So this is the smallest with respect to inclusion field of characteristic p, and then q, which is the smallest field of characteristic 0. And we get those as these fraction fields. Okay, so this was about functions, and now the second part will be about these vanishing sets, which we know. So how do we generalize these 0 loci and ideals? So let's say R is a ring, and you have any subset of R. Then we already defined in the context of affine varieties what is the 0 locus or the vanishing locus. And well, now that we have this evaluation, we can just take the same definition. It's just a set of all prime ideals, such that if you evaluate f at this prime ideal for all f in S, you get 0. And this is some subset of spec R. And then the converse map was, if you have a subset of R, then you can define its ideal as the set of elements of R, which evaluate at 0 at all the points of this subset. One remark here is that this evaluation map, which takes a function and spits out f of p, this goes from R to k of p, this is a ring homomorphism, right? This was this composition of these two ring homomorphisms above. And so going to 0 means you're in the kernel of this ring homomorphism. The kernel is always an ideal. And then, so you get an ideal, the set of F which vanish at one particular P is an ideal inside R. And then vanishing at all these points, you intersect all of the corresponding ideals. And taking the intersection of ideals is still an ideal. So I of X is really an ideal inside R. So, okay, this was the definition of vanishing locus and ideal. And just now some remarks, namely that a lot of the intuitions that we have about these things from the affine variety case still work. The first thing is that we can actually, in this spectrum, for the spectrum of R, we can give an explicit description of this in terms of intersections of ideals. Namely, well, we have seen f of p is 0 if and only if f is an element of p. And so this condition here, f of p equals 0 for all f in S, is equivalent to just saying f is in p for all f in S. And then you take the set of prime ideals satisfying this, but this is just equivalent to saying, well, this set S of elements that we chose, this is contained in the prime ideal P. So the vanishing set is basically defined by an inclusion of having all these elements included in the prime ideal. Okay, and here this ideal of X is even simpler, because then f of p equals 0 means f is in P for all P in X, but this is equivalent to just saying F is an intersection of all these P for P in X. So the ideal is just some intersection. So we see these are very natural formulas now, just in terms of inclusions and intersections of ideals. So that's useful for proving many of their properties. Then one more philosophical thing, like we have defined this evaluation f of p as first going from R to R modulo P and then going to this fraction field K of P. But somehow it seems like this last step, going to the fraction field, this was a bit redundant. We could also just have taken f of P as being an element in this R modulo P. This would still depend nicely on P itself. This is an integral domain. This is not so bad. So why didn't we do this? Why didn't we say this evaluation is just a value in here? Well, if we look a bit later in the lecture, there we are going to define what it means to be a regular function on some open subset of a scheme. And just as for affine varieties, the regular functions will locally look like G modulo F for some elements G and F in R. And then you see, if you evaluate this thing here at a point P, then, well, what we can do in this fraction field is we can evaluate G at P and divide by the value of F at P. And then we must make sure that this is not 0 in this field. But you see, in order to divide by F, we need to go to this fraction field. And so by going to the fraction field, we make sure that the values of these global functions in R at a point P and the values of these regular functions, they live in the same ring, namely in this fraction field. And so for this purpose, so that you can, for example, say, let me add f plus phi. This gives us a regular function, then its values is f of p plus phi of p. So that this makes sense, it's nice to work entirely with this fraction field. Okay. And then finally, this was a bit about the philosophy of the definition, and then just very basic properties that we have seen before, they still hold. So somehow just to record them here. So for example, the vanishing locus of some set S is the same thing as the vanishing locus of the ideal generated by S. This follows immediately from the formulas above. Then if you have a union of two vanishing loci, it's the same thing as the vanishing locus of the product. And you have an intersection of vanishing loci, an arbitrary intersection, in fact. It's just the vanishing locus of the union of all of these Si which you impose. The same formula held in the affine variety case. And then finally, the vanishing locus of 1. For example, if we wanted to prove this, then we would see it's a set of prime ideals containing 1, but any ideal which contains 1 must be the full ring, but a prime ideal must always be a proper ideal. It can never be the full ring. And so there's no such prime ideal, and so we get the empty set. And similarly, the vanishing locus of 0, well, 0 is contained in any prime ideal, and so you get the full ring spec R. Okay, and so you see these proving these properties is now just very basic ring theory, essentially. And so now that we have defined the vanishing loci, the next step will be defining the Zariski topology. And if you see these properties here, that somehow finite unions of vanishing loci are vanishing loci, and arbitrary intersections of them are still vanishing loci, and you get empty set and spec R, probably you can guess what will be the closed sets in the Zariski topology. Okay, but this is in the next video.